When charged objects are brought closer, they feel forces, what we call electrostatic force. But the question is, how does this force change in relation to the separation between the charged objects and the amount of charge they carry? To figure it out, in 1785, French scientist Charles Augustin de Coulomb conducted a series of experiments, and based on his observations and measurements, he articulated a law which we now call it Coulomb's law in his order. What did Coulomb discover through his experiments? How can we express his experimental findings in mathematical language? That's coming up. Let's start with the experiment itself. The primary objective of Coulomb's experiment was to determine the precise relationship between those variables. To do that, let's consider two charged particles Q1 and Q2, which are separated by a distance r. Now we have three independent variables to work with. We will vary one of them while keeping the other two fixed and observe the change in force that it can produce. Let's start with Q1 and keep Q2 and R fixed. According to the Coulomb's experiment, if Q1 is raised or lowered by a specific multiple, the force will also rise or fall by the same amount, which essentially implies that the relationship between the force and Q1 is linear. Mathematically, this relationship is denoted as F is proportional to Q1 when Q2 and R fixed. Due to symmetry, Q2 will follow the same relation as Q1, which is F is proportional to Q2 when Q1 and R fixed. Now let's move to the distance r. Experimental results indicated that if the distance doubles, the force will decrease by a factor of 4. On the other hand, if r is made 3 times shorter than before, the force will increase by 9 times. This means force has an inverse square relationship with r. Okay, so far we have discussed about the magnitude of the force. However, force is a vector quantity. What about its direction? Coulomb discovered that this electrostatic force always points along the line joining the two particles. Prior to Coulomb, two more facts were known, like charges repel, whereas opposite charges attract. Now that we know all the facts concerning electrostatic interactions, the next step is to combine all these separate parts into a single mathematical equation. Let's start with these three relations, and it's very much obvious that we can combine them into one according to the rules of proportionality. To turn it into an equation, we need to introduce a proportionality constant. Let's call it k. So we are done with the magnitude of force. Now it's time to add the direction. To do so, let's first define a unit vector along the line joining Q1 and Q2 and pointing away from Q1. Let's call it R12 hat. We will always use the symbol hat to represent a unit vector. Notice R12 is pointing outward. This is important. Using this unit vector, now we write the force acting on Q2 like this. Remember, unit vector has magnitude 1, so magnitude of the force will remain unchanged. Now this is a vector equation, so I put a vector sign on F12. Here the second digit denotes force on charge Q2 due to the interaction between charges Q1 and Q2. Finally, let's see if this vector equation agrees with our observations. For same charges Q1, Q2, either both positive or both negative, then their product Q1, Q2 is positive. Since k and r are always positive, k Q1, Q2 over r square is also positive. This means direction of force is the same as the unit vector we defined previously. As mentioned earlier, similar charges repel, which implies that force is pointing outward. So in this case, formula's prediction perfectly fits our observation. For the charges with opposite signs, product Q1, Q2 is negative. Using same argument as before, we can see that our formula indicates that force points in the opposite direction as the unit vector R12, implying that we have an inward force in this situation. And we already know that opposite charges attract. So this force points toward each other. This time formula's prediction also matches with our experimental observation. So in the end, we can say that this little vector equation we have completely describes electrostatic interaction. Now one of the issues in applying Coulomb's law is that this is an abstract expression and we would like to make one more version of it. To do so, we shall treat the distance r between charges as a vector from object 1 to object 2. Now notice that vector r12 and the unit vector r12 points both in the same direction. As we know that the unit vector is equal to the vector divided by its magnitude. So we can write r12 hat is equals to vector r12 divided by modulus of r12. Here modulus of r12 is same as r. Let's rewrite Coulomb's law using this expression. Vector r12 sometimes referred to as separation vector. Often we must work in a coordinate system where we are given position vectors of charges rather than their separation vector. To handle these cases, we shall alter our formula a little bit. Let's choose a coordinate system and specify its origin. Vectors r1 and r2 are position vectors of charges q1 and q2. Notice that this makes a nice little triangle with the separation vector r12. Applying vector addition rule on this triangle, and we get vector r1 plus vector r12 is equals to vector r2. After rearranging, we get r12 is equals to r2 minus r1. Now let's replace separation vector r12 by this new expression. Finally, we obtain this equation. Now let's talk about the constant k. In SI unit, this is usually written as 1 over 4 pi epsilon naught. This is because it simplifies electromagnetic equations. Here epsilon naught is called permittivity of free space. Its value is 8.85782 into 10 to the power minus 12. And this may be approximated as 10 to the power minus 9 over 36 pi. By putting it into our previous equation, we get k approximately equals to 9 into 10 to the power 9 meter per farad. Now the final comment about Coulomb's law is this is directly applicable only for point-like charges. The necessary modification of the formula for extended charged objects will be considered in upcoming videos. Okay, that's all for now. I hope you have learned something new. If so, give me a thumbs up, share with others. To get the notes, visit my Facebook page, link in the description. And of course, don't forget to hit that subscribe button. Not just subscribe, ring the bell so that you don't miss any upcoming videos. Let me know your thoughts in the comment section. I'll see you in the next video.